Hello and welcome back. So I want to finish off our topic 8 discussion here, talking about something that you've probably seen in math before, but maybe the definition that we're going to give in this course is slightly different. So I do want to go through and define these things, and then we're going to take a look at one application of a proof towards the end of this section. So the first thing I want to introduce is this thing called an inverse function. So if F is a one-to-one correspondence, that is, if F is a bijection, that is, if F is a one-to-one and onto function, then we can apply what's called an inverse to that function. It's denoted by F of minus one. So what that looks like is we have a set A, we have a set B, we have F, and then we denote this by F going the other way. Now, if F is a mapping from set A to set B, then F inverse is a mapping from set B to set A. Now, this is very important. Why is it that F has to be a bijection before we can define an inverse function that maps from the output back to the input? So hopefully we can attempt to answer this in the next couple of examples here. But the key here is that we are defining an inverse function. Okay, now remember our definition of a function. Every input has a unique output. So let's consider cases where F is not a bijection. So first, let's consider the case where F is not it's not onto. So let's say I have A, B, C, and then 1, 2, 3, 4. And you'll notice that here I can map something like this. Now, if I was to define an inverse for this function, I might say that, well, I can say F inverse of 1 is equal to A. I can say F inverse of 2 is equal to B, and F inverse 3 is equal to C. But then what is the F inverse of 4? Well, I don't know. There's no F inverse. So therefore, the inverse is actually not a function. So in this case, we say that this function is not invertible. Okay, so this is not invertible. Okay, so what about the case where it is not one to one? So what if I had a function like this, 1, 2, and then I had something like this? Well, again, we can say that the inverse of 1 is equal to A, but then the inverse of 2 is B and C. Well, again, this is not a function. So again, it is not invertible. Now, I want you to be very careful because this is not the definition that we have in math. Okay, so in math, we're just inverting based on an equation, like switching the order of x and y and then solving for y. So even though that is in theory how we can find the inverse, we first have to figure out that the inverse exists. Okay, so we have to convince ourselves that the inverse exists. All right. The second thing that I want to introduce here is the idea of a composition, which again, you've probably heard of in a math course or something like that. A composition is essentially taking a function after taking another function. So if we had a function g from set A to set B, so let's say we had a function g from set A to set B, and then we had a function f that goes from set B to set C, so this is f and this is g, we can now define a composition, and we're going to call this f composed with g. It is a function that maps from set A to set C. And the definition is that I take G and then I take F. Okay, so I take G and then I take F. So this is going to be a function that maps from set A to set C. So what we're really saying is that if G is a mapping, so all the inputs in A map to a unique item in B, and all the items in B map to a unique item in C, then the composition is also a function. So every input in A gives me a unique mapping to C. Okay, so that is the composition. Now, the key here is that if you take a look at the composition, sorry, the codomain of G, this must match the domain of F. Okay, so those two things must match. Now, once again, when you've talked about compositions in math before, you may not have considered this because everything in math, our universe, is a real number, right? So we don't really need to make a check that this codomain matches this domain. Instead, we just do the composition. But here, we have to know that in a general sense, when we talk about functions, that if there is a composition at all of f composed with g, codomain of g must match the domain of f. Otherwise, there's no composition. Okay, so please keep that in mind. That is the second thing, I guess, that I wanted to introduce here. So if we put these ideas together, okay, these two ideas together, we can form a kind of a property about inverses and compositions. So generally, if we take a look at a function that maps from set A to set B, and then we take a look at its inverse. So we have f and we have f inverse. So assuming that f is a one-to-one correspondence, there's going to be an inverse. So if we take, for example, f composed with f inverse, okay, what does that give me? So essentially, we're taking the f inverse first, and then we're taking f. Well, that means we're starting somewhere in B, right? We're starting from an element in set B. We're mapping over to A, and then immediately we're mapping back to B. But what item are we getting as an output? And the answer is we get the same as our input. Right, so I hope everyone sees this, right? We will get the same thing as our input. So you remember what we called this? We called this an identity or function. So an identity function needs a set that goes with it. So this is going to be the identity function for B. Now remember, the set says what are the elements that I'm doing the identity on, right? So what are the inputs? And that also tells me what the outputs are. So everything in B gets mapped back to B. Similarly, if we take f inverse composed with f, this is going to give me the identity of A, right? So I'm going to start with an item in set A, and then I'm going to take first the f, and then immediately I'm going to take the inverse, and that's going to get me back to A. So just remember this. This is a really important definition for the inverses and how they relate to the original functions. All right. So a couple more theorems, and then I'll get into a very quick proof here. So this theorem is actually one that's given in your textbook, so I'm not going to go through the details, but it is telling you that if you have three functions, set A, set B, set C, and set D, and we have a mapping that goes F, G, and H, and I want to compose all three of these functions together. So I want a function that maps from set A to set D, then the order of the composition doesn't matter. Okay, the order of the composition doesn't matter. So another way to say that is if I look at the left-hand side here, I can take H composed with G, right? And then, and then before that, I could take F. So this jump is going to be the same as this jump. So G composed with F, and then H. This is the right-hand side. So the theorem says, once again, that if I compose three functions or more, that the order of the composition doesn't matter. Okay, those functions will always be equal. Now, just for a second, what does it mean that they're equal? What does it mean that two functions are equal? Well, in short, it means that whatever input that you give, the output will be the same. Okay, so for both of these functions, whatever input you give, the outputs will be the same. Okay, that is the definition of equality for two functions. So again, if you want the full proof of this theorem, please consult the textbook. I'm not going to go through the full proof here. Now, instead, I'm going to show you another theorem, which is that if I have set A and set B, and there is an inverse here, okay, so f does have an inverse. And also if I have a set C that that we have a mapping for G and G inverse, so both f and G here have inverses, then the composition of G and F also has an inverse. So the composition, right? So this is G composed with F. And so if I wanted the G composed with F inverse, it is the same by taking the individual inverses. Okay, I hope you can see this in this diagram. Again, the full proof is in your textbook. If you want to refer to that, please do, but I'm not going to go through the full proof here. Instead, I want to take a look at the last statement here, and I want to prove that instead. Now, before I do this, I want to recall what is the definition of uniqueness, okay? Because the statement here is saying if F has an inverse, then it is unique. Oh, by the way, what is it? It is referring to the inverse. Okay, so if the function F has an inverse, the inverse is unique. It's unique to F. Okay, so another way to say that is if a function has an inverse, that function has only one inverse. Okay, it cannot have more than one inverse. This inverse is unique. Now, what does uniqueness mean again? So remember when we defined uniqueness, we said there's two things that we need to define. Number one, we need to say that it must exist. Okay, so uniqueness, the word unique, number one, means it exists. Number two means that if there are two of them, then those two are going to be equal. And we said, so how do we say this? There exists the object. Okay, that's the first definition of unique. And then the second definition of it is if there's two objects, then they must be the same. Okay, and at the time, we said that the first definition is that there must be greater than or equal to one of them. And the second definition is that there must be less than or equal to one of them, right? So there's at least one and there's at most one. Okay, that is the definition of uniqueness. Okay, so now that we've reviewed that, let's go on and try to prove that last statement. And I want you to see that the first statement is already proven. So F, you're told already that F has an inverse. So does it exist? Yeah, it exists. So this part is done already. What's left of this proof is I need to show that if there are two inverses, that those two inverses better be equal. Okay, so I'm going to so my goal, once again, I'm not going to write this down, but my goal, once again, is to show that if I have two inverses, they must be equal. So let's assume, so here's my proof. Let's assume that F has two inverses. And those two inverses we'll call F inverse 1 and F inverse 2. Now, since they are both inverses, what we can determine from that is F composed with F inverse 1, sorry, F inverse 2 is equal to the identity of B. Okay, so let's check whether or not that's true. So F composed with the F inverse is always the identity of B, right? So if F inverse 2 is in fact an inverse, this must be true, right? I hope everyone's okay with that. Also, F inverse 1 composed with F must be the identity of A. And again, let's check that. So any inverse composed with F must be the identity of A. So both of those statements must be true. Now, at this point, you might be asking, well, wait a minute, what about the other variations, right? What about F composed with F inverse 1? Is that equal to identity of B? Yes, it is. I just don't need it for this proof. Okay, so let's consider what F inverse 1 is. Now, do you agree that F inverse 1 is equal to F inverse 1 composed with the identity of A? Now, if you take a second here, just to draw a picture on the side, I'm just going to draw it really small up here. So I have a set A and a set B, and I have F and I have F inverse. Now, if I took an F inverse, if I took an input, if I took an F inverse to this point, And then immediately I took the identity of A, which means I mapped the object back to itself. Do you see that those two outputs are the same? Okay, so if I just took the inverse versus if I took the identity of, sorry, not identity of A, my mistake, the identity of B. So I took the identity of B first and then took the inverse. Do you agree that they are the same? They end up in the same place. They end up as the same result. Okay, so those two should be equal. All right, so now what is the identity of B? Well, let me just substitute this part in there. All right, so the identity of B, I can substitute as F composed with F1, F minus 1 of 2. All right, so I just made that substitution. Now, the next step is that we are composing three functions together. Anytime we compose three functions together, I can move the bracket however I want. This was the theorem that we just discussed up here, which we didn't prove, but it's true. So we can move the bracket over like so, and they must be equal as well. All right, next. This is nothing more, so this bracket here is nothing more than the identity of A. So if you take a look at this thing that we have up here, we can substitute the identity of A for F inverse 2. So again, let's take a look at uh, our, our chart over here. So if I took an inverse, so if I took an inverse and then I take the identity of A, well, it should be the same as our original inverse, right? So I hope you can see that all of these are equalities. All of these are the same function. And then we've shown that if inverse 1 must be equal to f inverse 2. So what we can conclude here is that there is at most one inverse. Okay, so there's at least one inverse and there's at most one inverse. Therefore, inverse is unique. Okay, so I hope everyone was able to follow that. I just wanted to really use this opportunity to make a uniqueness proof. Okay, so whenever you need to prove something is unique, the first thing we're going to do is assume that there's two of them, and then show that they must be equal. Or we're going to assume that there's two of them, and then show that this can never happen. Okay, so we're going to assume that there's two different ones, and then show that this could never happen. So there's another way that we can show uniqueness. So two parts, right? We show that there's at most one, and also we need to show that there's at least one. Now in this proof, again, we're told that there's at least one, so we didn't need to make that proof. Okay, so this concludes our topic 8. I think this is a good time to stop our video again. So when we come back, we're going to jump into topic 9, and we're going to talk about something a little bit new. So I'll see you in the next video.